welcome back. I'm glad you've returned to the silence. We leave the familiar behind to witness the silent beauty of the cosmos as we begin our long, drifting journey toward Io, the volcanic jewel locked in the fierce embrace of Jupiter. As we drift closer through the freezing void, the immense presence of the giant planet begins to fill our vision, its swirling bands of amber and cream casting a surreal glow upon its innermost large moon. We are approaching a place where the laws of planetary geology are pushed to their absolute limits, a celestial body no larger than our own companion moon, yet possessed of a restless, churning interior that defies expectation. This is a realm of perpetual transformation, where the surface is constantly rewritten by rivers of molten rock and towering plumes of sulfur that rise high into the blackness of space. To truly understand this hyperactive world, we must look beyond the outer crust and feel the invisible, colossal forces that shape its very destiny. At the heart of this cosmic drama is a gravitational tug-of-war of unimaginable scale, a silent battle fought across millions of miles of empty space. Io finds itself trapped between the immense gravitational pull of Jupiter on one side and the rhythmic, steady tugs of its sibling moons, Europa and Ganymede, on the other. This orbital dance forces Io into an eccentric, elongated path, meaning its distance from the giant planet changes constantly as it races through its quick orbit. Imagine a world being squeezed and stretched like clay by invisible hands, its solid ground rising and falling by hundreds of feet during every single revolution. This constant, relentless flexing generates an incredible amount of internal friction, melting the deep rock into a subterranean ocean of magma that desperately seeks an escape. What results from this endless friction is a landscape of pure, unbridled power, making this distant moon the most volcanically active body in our entire solar system. Hundreds of massive volcanic vents scar the surface, erupting with a fury that completely outmatches anything found on Earth. Plumes of sulfur dioxide shoot hundreds of miles into the freezing vacuum, cooling into a delicate, colorful snow that blankets the plains in shades of yellow, green, and white. There are no ancient impact craters to be found here, as the relentless flow of lava resurfaces the entire moon every few millennia, erasing its past to paint a new masterpiece of volcanic architecture. It is a brilliant paradox of the cosmos, a place where the bitter cold of deep space meets the white-hot intensity of a world turned inside out by gravity. As we prepare to observe the specific mysteries of this volatile sanctuary, we begin to realize that this moon is not just a passive rock, but a living dynamo interconnected with Jupiter itself. The volcanic gases escaping into space become charged by the intense radiation, forming a vast, invisible cloud of plasma that glows with energetic particles. This connection creates powerful electrical currents that flow directly between the moon and the gas giant, sparking intense auroras in the upper atmosphere. We stand on the precipice of a profound journey through the many truths of this volcanic wonderland, ready to explore every river of liquid sulfur, every towering mountain peak, and every whisper of its magnetic soul. Let us sink deeper into the cosmic dark, letting the rhythm of these distant forces guide our thoughts across the sulfur plains of this magnificent, burning world. We must begin our detailed exploration by looking back to the moment humanity first noticed this restless spark in the dark, a discovery that fundamentally shook our understanding of the universe. In the early days of 1610, the astronomer Galileo Galilei pointed his basic telescope toward the immense light of Jupiter and noticed tiny, moving points of light dancing around the giant planet. One of these points was Io, the closest of the major satellites, positioned just a few 100,000 miles away from the swirling clouds of the gas giant. This discovery was truly revolutionary because it proved beyond a doubt that the Earth was not the center of all motion in the cosmos, revealing a smaller world bound tightly to a massive master. As the centuries passed, astronomers continued to watch this tiny speck of light, completely unaware of the violent secrets hidden beneath its distant, glowing surface. Today, we understand that this close proximity to Jupiter sets the stage for everything that occurs on its volatile, ever-changing landscape. When we compare this hyperactive celestial body to the familiar worlds closer to home, we find a fascinating paradox in its physical dimensions. Io is roughly the same size as the Earth's moon, possessing a familiar scale that makes its extreme behavior all the more astonishing to contemplate. Yet, unlike the icy satellites that inhabit the cold outer solar system, this world is remarkably dense, ranking as the most dense moon known to science. Its internal structure is composed primarily of heavy silicate rock, surrounding a massive core of iron or iron sulfide, creating a heavy world wrapped in a thin crust. This high density tells a profound story of a world that was baked dry long ago, completely stripped of the lighter water ice that defines its neighboring companions. By studying its unique weight and composition, scientists have realized that Io behaves more like a rocky planet of the inner solar system than a typical moon of a gas giant. The true secret behind the intense energy of this world lies not within its own rocks, but in a beautiful mathematical lock known to astronomers as the Laplace resonance. This orbital arrangement links Io with its celestial neighbors, Europa and Ganymede, in a repeating pattern that has persisted for billions of years. For every single orbit that the distant, icy Ganymede completes around Jupiter, the bright moon Europa completes exactly 2 orbits, and Io completes exactly 4. This rhythmic alignment means that the moons pass close to each other at regular, predictable intervals, giving each other a subtle gravitational tug that keeps their paths elongated. It is this constant synchronization that prevents Io from ever settling into a peaceful, perfectly circular path around its massive parent planet. Without this precise orbital dance with its sister moons, the inner fires of Io would have cooled long ago, leaving it as a quiet, frozen rock. Because this mathematical resonance forces the moon into an elongated, elliptical orbit, the gravitational pull it experiences from Jupiter fluctuates dramatically. As it sweeps closer to the immense mass of the gas giant, the planet's gravity pulls fiercely on the moon, stretching its solid shape into a slight oval. Then, as it drifts further away along its path, the grip relaxes, allowing the rocky sphere to snap back into a more rounded form. This continuous, relentless squeezing causes the solid crust of the moon to rise and fall by up to 100 meters during every single revolution. The sheer scale of this movement creates an immense amount of internal friction, turning solid rock into a churning subterranean sea of liquid magma. We can think of it as a world constantly flexing under the weight of an invisible giant, generating endless heat from the inside out. This constant generation of internal friction transforms the moon into the most volcanically active body in our entire planetary system, completely overshadowing the geological activity of Earth. Even though it is a fraction of the size of our home planet, it produces over 100 times more volcanic energy and material every single year. The interior is so intensely heated that it acts like a planetary pressure cooker, constantly searching for any weakness in the crust to release its staggering energy. Hundreds of massive volcanoes pierce the surface, erupting simultaneously and rewriting the rules of planetary geology with every passing hour. It is a world where the quiet peace of space is met with a continuous, overwhelming display of primal heat and motion. As we watch from afar, we realize that this hyperactive state is the only way the moon can survive the crushing forces exerted by Jupiter. As we observe the unique features of this scorched landscape, we notice a complete absence of the water ice that defines almost every other body in the outer solar system. While nearby Europa is wrapped in a frozen ocean, and Ganymede possesses vast sheets of ice, this volcanic moon is almost entirely dry. Billions of years of continuous volcanic activity and intense radiation have systematically stripped the moon of any volatile water molecules that it might have once possessed. The extreme heat from within has driven these lighter materials out into space, leaving behind a parched world composed entirely of rock and heavy chemical compounds. This lack of ice allows the steep volcanic mountains and vast lava plains to retain their stark, rugged shapes without sliding or melting away. It stands as a lonely, rocky desert in a region of space otherwise dominated by ice and water. One of the most surprising discoveries made by modern spacecraft was the total absence of impact craters across the entire surface of this restless moon. In a solar system where most ancient bodies are heavily scarred by billions of years of asteroid encounters, this world appears completely unblemished by cosmic debris. This pristine appearance is not because the moon avoids being struck, but because its volcanic activity operates on a truly staggering timescale. The continuous flow of fresh liquid lava resurfaces the entire moon so rapidly that any new crater is quickly filled, buried, and completely erased from view within a historical blink of an eye. The surface we see is incredibly young, constantly renewing itself to wipe away the scars of the past and present a clean canvas to the cosmos. This continuous self-cleansing makes Io one of the few places in the universe that completely hides its own evolutionary history. Humanity first witnessed the true nature of this volcanic powerhouse in 1979 during a historic flyby by the Voyager 1 spacecraft. A navigation engineer working on the mission noticed a strange, faint shadow rising off the edge of the moon in one of the processed images. Upon closer inspection, scientists realized they were looking at an enormous, umbrella-shaped plume of gas and dust shooting hundreds of miles into the airless void. This marked the very first time that active volcanism had ever been observed on another world beyond the boundaries of Earth, forever changing our perspective on the planetary systems. It proved that the outer solar system was not a collection of dead, frozen rocks, but a dynamic arena of active forces that could rival our own planet. This single discovery shattered old theories and ignited a new era of deep space exploration focused on tidal energy. The environment presents some of the most dramatic temperature extremes found anywhere in the known universe, creating a landscape of ultimate contrasts. The ambient temperature across the surface is bitterly cold, dropping to a freezing -140 degrees Celsius, because the moon sits so far from the warmth of the sun. Yet, breaking through this frozen crust are vast lakes of molten silicate lava that can reach temperatures higher than 1,300 degrees Celsius. This means that a traveler standing on the surface would experience a realm where glowing, white-hot rivers of rock flow directly alongside fields of frozen sulfur snow. It is a continuous clash of fire and ice, existing in perfect balance under the dark sky of Jupiter. This extreme temperature difference creates a strange thermal signature that radiates out into the cold void of space, whispering tales of its intense inner fire. The sheer volume of material erupted by these hundreds of active vents is so immense that it completely changes the geography of the moon on an annual basis. Scientists estimate that the rate of volcanic deposition is high enough to bury the entire surface under a fresh layer of volcanic ash and lava several millimeters thick every year. Over the course of just a few millennia, this steady accumulation builds a completely new crust, recycling the older rock back down into the molten interior. This continuous cycle means that the features mapped by spacecraft just a few decades ago have already shifted, evolved, and changed their shapes. We are observing a world without a permanent memory, a canvas that is constantly painted over by the creative and destructive forces of gravity. It reminds us that change is the only constant in this dynamic corner of the solar system, where a moon remains forever young by consuming itself. When we examine the actual architecture of these alien volcanoes, we discover that they do not resemble the majestic, conical peaks found on Earth or Mars. Instead, the landscape is dominated by unique features called pattery, which are massive, flat-floored volcanic depressions surrounded by steep walls. These structures form when giant chambers of magma beneath the surface empty out completely, causing the overhead ground to collapse down under its own immense weight. The result is a series of colossal, sunken cauldrons that regularly fill with lakes of liquid rock, acting as the primary vents for the moon's internal fury. This flat geometry shows how easily the thin, fragile crust breaks under the intense stress of Jupiter's continuous tidal flexing. It creates a surreal skyline where volcanic power is expressed not through towering summits, but through deep, glowing wounds in the earth. Among these deep volcanic wounds, the absolute giant of the moon is a monstrous feature known to astronomers as Loki Patera. This immense volcanic depression is wider than many large terrestrial seas, stretching across more than 200 kilometers of the parched landscape. It behaves like a gigantic, unstable lava lake, covered by a thin crust of cooling rock that periodically fractures and sinks back into the depths. Scientists have observed that this massive lake undergoes predictable cycles of brightening and dimming, a rhythmic overturning that occurs over the course of several hundred days. When the old crust breaks apart, a wave of fresh, incandescent lava sweeps across the entire basin, releasing a massive surge of thermal energy into the cold void. Watching this feature from space provides a clear window into the titanic scales of energy shifting just beneath the moon's surface. The striking palette of colors that blankets this celestial body is a direct consequence of the diverse forms of sulfur erupted from its deep interior. As liquid sulfur is heated to different temperatures and then quickly chilled by the freezing vacuum of space, its molecular structure changes dramatically. These distinct variations, known as allotropes, paint the landscape in a vivid mosaic of bright yellows, deep reds, dark blacks, and pale greens. The areas immediately surrounding active vents are often stained a deep, rusty red, indicating the presence of unstable sulfur chains created by intense heat. Meanwhile, the older, cooler plains fade into a soft, creamy yellow as the chemical elements settle into their most stable forms over time. This creates a brilliant, shifting canvas that allows scientists to map the surface temperature history simply by studying the distribution of its colors. Despite the chaotic violence of its volcanic eruptions, Io manages to hold onto an incredibly thin, ghostly atmosphere composed almost entirely of sulfur dioxide gas. This fragile envelope of air is not permanent or stable, but instead exists in a constant state of collapse and rebirth driven by the daily cycle of warmth and shadow. During the day, the faint sunlight warms the surface frost just enough to cause it to sublime, turning directly from solid ice into a thin vapor that rises above the plains. When the moon slips into the colossal shadow of Jupiter, the temperature plummets instantly, causing the entire atmosphere to freeze and fall back to the ground like a delicate blanket of toxic snow. This means the air itself is an ephemeral creation, breathing in and out as the world moves through the alternating cycles of light and dark. Another legendary feature that defines the identity of this world is the hyperactive volcanic center named Peel, famous for its grand scale and distinctive visual footprint. This particular vent produces a continuous, high-speed plume of gas and dust that rises hundreds of miles above the surface before cascading back down in a giant arc. The falling material creates a massive, perfectly symmetrical ring of red sulfur dust that spans more than 1,000 kilometers in diameter, easily visible from distant spacecraft. This iconic red ring acts like a permanent target painted on the face of the moon, marking a region of intense, non-stop geological activity. The sheer constancy of this eruption over decades of observation proves that some of Io's internal plumbing systems are stable, deeply rooted pathways connected to an inexhaustible supply of magma. The mechanics of how these spectacular volcanic plumes rise into space reveal the profound influence of the moon's low gravity and lack of air. Without a thick atmosphere to slow them down, gas and dust particles shoot out from the vents at speeds exceeding 1 kilometer per second, which is several times faster than a speeding bullet. These particles fly upward in clean, graceful ballistic paths, unimpeded by friction, until they reach the peak of their trajectory and spread outward like a giant umbrella. Because the moon's gravity is only a fraction of Earth's, these plumes can easily reach heights that would extend well into the upper reaches of our own atmosphere. This creates a hauntingly beautiful sight where vast, silent fountains of matter hang suspended over the horizon for hours before drifting gently back to the multicolored soil. While one might expect all the high peaks on this hyperactive moon to be volcanic cones, the tallest mountains are actually formed by a completely different process of massive tectonic compression. As the endless layers of fresh volcanic material bury the older surface, the crust is constantly forced downward into a smaller, tighter space deep within the moon. This intense downward pressure squeezes the underlying rocky crust horizontally, forcing colossal blocks of silicate rock to fracture and thrust upward into the sky. Some of these non-volcanic, jagged mountains reach heights of up to 17 kilometers, which is nearly twice the altitude of Mount Everest on Earth. These towering, tilted blocks stand as silent sentinels amidst the flat lava plains, showing that the moon experiences immense structural stress that can shatter solid rock on a continental scale. The composition of the liquid rock that flows across these plains reveals a world operating at temperatures that have not been seen on Earth for billions of years. Analysis of the thermal radiation emitted by the active flows shows that they consist of ultramafic silicate lava, which is exceptionally rich in magnesium and iron. This specific type of lava requires incredibly high temperatures to melt, often flowing at more than 1,600 degrees Kelvin. On our modern Earth, the interior has cooled sufficiently that such high-temperature eruptions are a thing of the distant geological past, making Io a living laboratory for studying the early history of rocky planets. The liquid stone flows with a consistency closer to water than thick mud, allowing it to rapidly flood vast areas and create immense, glowing sheets of fire that reshape the geography overnight. When these high-temperature silicate magmas breach the surface, they often do so along immense tectonic cracks, creating spectacular phenomena known as lava curtains. Instead of erupting from a single, isolated point, the molten rock erupts simultaneously along a line that can stretch for tens of kilometers across the darkening plains. This creates a literal wall of liquid fire rising dozens of meters into the airless void, illuminating the surrounding sulfur deserts with a fierce, flickering radiance. As the eruption progresses, the energy often concentrates into a few specific points along the fissure, turning the continuous curtain into a series of isolated, high-volume fountains. The remnants of these events leave behind long, dark scars on the landscape, marking the places where the very fabric of the crust tore open under the strain of Jupiter's gravity. Beyond the physical surface of the moon lies another hidden danger: a relentless bombardment from the intense radiation belt generated by Jupiter's magnetic field. Io orbits deep within the heart of this invisible magnetosphere, where trapped electrons and ions whip around the planet at near the speed of light. This constant stream of high-energy particles strikes the moon's surface and atmosphere with immense force, stripping away atoms and molecules in a process called sputtering. This violent interaction creates a lethal environment that would quickly destroy any conventional electronics, presenting a major challenge for the robotic explorers we send to study this world. Yet, this destructive bombardment is also a creative force, transforming the escaped volcanic gases into a glowing, electrified ring of plasma that follows the moon along its orbital path. The electrified ring of plasma created by the moon's escaped gases forms a massive, donut-shaped cloud that encircles Jupiter along Io's orbital path. This structure, known to scientists as the plasma torus, glows intensely in ultraviolet light and spans a region of space far larger than the gas giant itself. As Jupiter rotates rapidly every 10 hours, its immense magnetic field sweeps through this cloud, accelerating the trapped ions to incredible velocities. This interaction creates a giant cosmic generator, producing a continuous electrical potential of 400,000 volts across the moon's diameter. The energy flowing through this torus is so immense that it constantly strips away more than a ton of material from the moon every single second, distributing its volcanic signature throughout the entire Jovian system. This invisible bridge of energy binds the moon to its master in a permanent, electrical embrace that influences the entire space environment around them. Deep within the northern hemisphere of this restless world sits a powerful and unpredictable volcanic center known as Sirte. This particular volcano is famous for producing one of the most energetic thermal outbursts ever recorded by modern astronomy, releasing a staggering amount of heat during its active phases. The eruptions at Sirte are characterized by massive fountains of ultramafic lava that shoot high above the fractured crust, completely altering the local topography in a matter of days. Unlike the brightly colored sulfur deposits found elsewhere, the area surrounding this vent is coated in dark, heavy silicate ash that stands out sharply against the vibrant plains. It serves as a reminder of the raw, primordial forces operating deep within the moon, capable of unleashing sudden explosions that can be seen across millions of miles of empty space. This stark contrast of dark ash on bright yellow ground highlights the intense diversity of materials erupting from the moon's deep interior. The physical nature of the moon's surface material creates an unusual phenomenon where the ground possesses incredibly low thermal inertia. Because the landscape is covered by porous layers of fine sulfur dust and loose volcanic ash, it has almost no ability to store or retain heat from the distant sun. The moment a region turns away from the sunlight and plunges into the darkness of night, the ground temperature drops instantly by more than 100 degrees Celsius. This rapid cooling creates intense thermal stresses within the crustal rocks, causing microscopic fractures to spread across the plains as the materials contract in the sudden cold. It is a world that lives in a state of thermal shock, experiencing violent temperature swings every few hours as it races along its quick path around Jupiter. This continuous cycle of heating and cooling shatters the surface materials into even finer grains, feeding the endless fields of cosmic dust. During its multi-year mission in the late 1990s, the Galileo spacecraft performed a series of daring close flybys that allowed scientists to probe the deep interior of the moon using radio signals. By carefully measuring how the spacecraft accelerated under the moon's gravitational pull, researchers were able to map the distribution of mass within the rocky sphere. These precise calculations confirmed that Io possesses a massive, distinct core made of iron and nickel that accounts for nearly 20% of its total weight. Furthermore, the data strongly suggested the existence of a global, interconnected magma ocean layer buried dozens of kilometers beneath the solid crust. This molten reservoir acts as a fluid cushion, allowing the outer shell to flex even more dramatically under the rhythmic tug of Jupiter's immense tidal forces. This hidden sea of liquid stone is the engine that drives the entire surface circus, ensuring the volcanic fires never run out of fuel. When planetary scientists mapped the positions of the hundreds of active vents across the moon, they discovered a strange and unexpected asymmetry in their global distribution. Instead of being spread evenly across the surface, the active volcanoes are significantly more concentrated on the hemisphere that faces away from the direction of orbital motion. This trailing hemisphere features a higher density of persistent thermal hotspots and massive lava lakes, while the leading hemisphere appears relatively quiet by comparison. Astrophysicists believe this uneven pattern is a direct result of how the internal tidal dissipation concentrates heat within specific zones of the mantle. It shows that the cosmic geometry of its orbit dictates exactly where the crust will tear open, forcing certain regions to bear the brunt of the internal melting. This structural imbalance creates a world of two halves, where one face is permanently more scarred by fire than the other. While sulfur dioxide remains the dominant component of the giant volcanic plumes, sophisticated spectrometers have detected a rich variety of trace elements mixed within the escaping gases. Small amounts of elemental sodium, potassium, and chlorine are continuously blasted into space, creating a vast, glowing cloud of neutral atoms that surrounds the moon. This atomic cloud extends for millions of kilometers into the Jovian system, trailing behind the moon like the glowing tail of a permanent comet. The presence of these specific elements tells a detailed chemical story of a mantle that has undergone intense, repeated processing over billions of years of geological activity. As these atoms interact with the sunlight, they scatter light in a way that allows observers on Earth to trace the invisible tendrils of Io's breath stretching across the dark void. This halo of glowing gas adds an ethereal, ghostly dimension to the otherwise harsh and rocky environment of the inner moon. Among the many mysteries of this volatile world is the existence of a unique class of eruptions known to researchers as stealth plumes. These fascinating phenomena consist almost entirely of pure, clear gas without the heavy dust particles that typically reflect sunlight and make a plume visible to cameras. Because they lack the reflective ash, these eruptions remain completely invisible to standard optical instruments, quietly pumping massive amounts of sulfur dioxide into space without leaving a visual trace. Scientists can only detect their presence by observing how they block the light of distant stars, or by measuring the sudden drop in temperature they cause as the gas expands and cools. These hidden fountains prove that the moon is even more geologically active than it appears, silently reshaping its atmosphere through unseen vents scattered across the frozen plains. They remind us that the most significant changes in the cosmos often happen in utter silence and hidden from plain sight. Near the northern polar region lies a spectacular chain of volcanic cauldrons known as the Tivashter Pattery, a place of unparalleled geological drama. This region became famous when robotic explorers captured a massive, multi-kilometer-long curtain of liquid fire erupting from a giant fissure within the depression. The molten rock fountains reached heights that completely dwarf any similar event in human history, illuminating the dark polar night with a fierce, primeval glow. Over the course of several months, the sheer volume of lava released by this fissure created a massive new lake of liquid stone that slowly filled the surrounding basins. The observation of T. Vastor provided definitive proof that the moon's polar regions are just as vulnerable to the internal heating forces as the equatorial zones, shattering early models that predicted a quieter environment near the poles. It stands as a testament to the inescapable reach of Jupiter's gravity, which melts the moon uniformly from core to crust. The dramatic cycle of atmospheric collapse and rebirth creates powerful global wind systems that sweep across the colorful plains at incredible speeds. As the sun rises over the horizon, the sudden sublimation of sulfur dioxide frost creates a localized high-pressure zone on the day side of the moon. This gas rushes toward the incredibly cold, near vacuum of the night side, where the atmosphere is constantly freezing out onto the dark ground. The resulting pressure difference drives howling winds that can reach speeds of hundreds of kilometers per hour, carrying fine particles of sulfur dust across the landscape. Even though the air is exceptionally thin, these fast-moving winds are capable of slowly drifting the volcanic ash into long, subtle streaks that can be seen from orbit. It is a weather system driven not by moisture or air pressure in the traditional sense, but by the raw transition between solid frost and ethereal gas. The endless accumulation of fine volcanic ash and sulfur dust has created vast, incredibly smooth expanses known to geologists as the plains units. These flat terrains cover more than 60% of the moon's surface, acting as a soft, colorful matrix that fills the spaces between the jagged mountains and deep volcanic pits. The material that forms these plains is continuously supplied by the falling debris of the giant plumes, which rains down over millions of square kilometers in a gentle, toxic snowfall. This constant accumulation buries any small structural faults or rugged lava flows, smoothing out the topography into a deceptively peaceful landscape. When viewed from a distance, these plains appear like a vast, serene ocean of cream and pale yellow, completely hiding the violent tectonic strains that simmer just a few kilometers beneath the dust. They offer a moment of visual rest in an otherwise chaotic world, a smooth blanket resting over a heart of pure fire. The invisible electrical connection between the volcanic moon and Jupiter manifests as a monumental structure known as the Io flux tube. This magnetic pipeline carries millions of amperes of electrical current through space, creating a direct circuit between the moon's ionosphere and the polar regions of the gas giant. As Io cuts through Jupiter's rapidly rotating magnetic lines, It excites powerful plasma waves, called Ulfane waves, that travel along this tube at incredible speeds. When these waves finally strike Jupiter's upper atmosphere, they trigger brilliant, localized glowing spots within the planet's auroral rings. This glowing footprint moves in perfect synchronization with the moon's orbital motion, a distant testament to the profound energy transfer occurring across the void. It demonstrates that the volcanic moon is not an isolated world, but an active component of a larger planetary machine. Among the many persistent features monitored by space scientists, the volcano named Prometheus stands out as a marvel of geological stability. First observed by the Voyager spacecraft as a bright plume, this remarkable vent has been erupting continuously for over 4 decades, without ever losing its strength. The plume itself is driven by a unique mechanism where a slow-moving lava flow advances over fields of pre-existing sulfur dioxide frost. As the hot silicate rock touches the frozen ground, it vaporizes the moisture instantly, causing localized gas explosions that feed the beautiful, umbrella-shaped cloud above. This continuous interaction creates a shifting plume base that slowly tracks the forward progress of the underlying lava field across the plains. It provides a fascinating look at how different geological forces cooperate on this world, using volcanic heat to recycle the frozen surface into the sky. While sulfur dioxide forms the bulk of the gaseous emissions, astronomers have also detected the elusive presence of sulfur monoxide within the active plumes. This highly reactive chemical compound is incredibly rare on Earth because it quickly breaks down or bonds with other elements in a thick atmosphere. In the near vacuum of Io, however, these molecules can survive long enough to be identified by their specific infrared light signatures. The presence of sulfur monoxide indicates that the volcanic vents are operating under extreme chemical conditions, where intense heat breaks apart more complex molecules before they can escape. This chemical fingerprint gives scientists crucial clues about the exact oxygen levels present within the deep magma chambers. It allows us to peer metaphorically into the hidden depths of the moon, decoding the atomic recipes that boil beneath the crust. The patterns left behind by falling volcanic debris create magnificent, widespread circular deposits that stain the surrounding landscape. These rings of pyroclastic material are composed of fine dust grains that reflect light in distinct ways, depending on how fast they cooled during their flight through space. Around many vents, we observe bright white halos of pure sulfur dioxide frost that contrast sharply with the yellow plains. Closer to the central vents, dark gray and black deposits mark the landing sites of heavier silicate ash and rich glass droplets. These dark materials represent the primal crust being shattered and expelled by the expanding gases during violent eruptions. By mapping these concentric rings of varying color and texture, researchers can trace the history of individual eruptions, reading the rings like the growth lines of a planet. In early 2007, the New Horizons spacecraft performed a rapid flyby of the Jovian system, capturing breathtaking new views of Io's ever-changing face. As the probe rushed past on its long journey to the outer solar system, its advanced cameras witnessed a spectacular 500-kilometer-high plume rising from the northern polar volcano, Tvashter. The incredible clarity of these images allowed scientists to observe the fine structure of the plume, revealing complex filaments and waves rippling through the expanding gas. This encounter confirmed that the moon's volcanic engines were operating with undiminished power, showing no signs of cooling down over decades of human observation. The data gathered during this brief visit provided a vital snapshot of a world caught in a state of permanent crisis, forever shifting its shapes between the visits of human machines. When scientists calculated the total amount of thermal energy radiating from the moon's surface, they arrived at a staggering number that surprised the scientific community. The global heat flow of Io is significantly higher than the heat produced by the radioactive decay of elements inside standard rocky planets like Earth. This immense excess of energy can only be explained by the continuous action of tidal heating, proving that gravitational friction is the dominant geological force in this region of space. The planet radiates this heat through hundreds of localized hotspots, creating an efficient cooling system that prevents the entire moon from melting completely. This high heat output means that the moon is constantly losing energy to the cold void, requiring a continuous supply of orbital friction to keep its inner fires burning. It stands as a profound reminder of how gravity can substitute for solar warmth, transforming a distant, frozen rock into a world of pure thermal dynamics. The immense jagged mountains that pierce the sky do not remain stable forever, but instead undergo spectacular processes of structural failure and collapse. Because these peaks are subjected to continuous seismic tremors caused by the nearby volcanic eruptions, their steep slopes are highly unstable. Over time, the intense stress causes giant sections of solid rock to fracture and break away, generating colossal landslides that sweep across the flat plains. The debris fields left behind by these collapses can extend for tens of kilometers from the base of the mountains, creating vast fields of shattered rock. In some areas, the sublimation of underlying sulfur layers can undermine the foundations of these mountains, causing entire peaks to slowly sink or tilt into the surrounding plains. This creates a highly dynamic topography where even the grandest mountains are slowly ground down and consumed by the restless environment. Another extraordinary feature that defines the scale of this world's volcanism is the massive flow field known as Amirani. This immense volcanic system represents the longest active lava flow ever observed anywhere in our solar system, stretching across hundreds of kilometers of the colorful landscape. Unlike the explosive eruptions that form towering plumes, Amirani behaves like a steady, oozing wound that constantly pumps liquid silicate rock across the plains. The lava moves through a complex network of underground tubes and surface channels, breaking out in fresh breakouts that slowly widen the dark field. This style of continuous, low-intensity volcanism helps to distribute heat evenly across large areas, contributing significantly to the global resurfacing process. Observing Amirani allows scientists to study the long-term behavior of massive lava fields, providing insights into how the ancient volcanic plains of Earth and the Moon were formed. The meeting point between advancing liquid lava and the global layer of sulfur dioxide frost creates an incredibly volatile environment. When a stream of molten silicate rock flowing at over 1,000 degrees Celsius encounters a field of frozen frost at -100 degrees, the reaction is instantaneous and violent. The extreme heat causes the frozen sulfur dioxide to flash immediately into a high-pressure gas, bypassing the liquid state entirely. This sudden expansion triggers powerful phreatomagmatic explosions that can blast craters into the advancing lava flow and rip open the solid ground. The expanding gas shoots fragments of rock and bright sulfur dust high into the airless sky, creating unique, localized miniature plumes along the edges of the flow. It is a continuous battle between the intense heat of the interior and the bitter cold of space, played out in a series of quiet explosions across the desert. The interactions between the Moon's thin atmosphere and the harsh radiation environment create a unique, highly conductive layer of air known as the ionosphere. This electrified envelope is filled with charged ions and free electrons that are constantly stripped from the volcanic gases by the impact of solar ultraviolet light and Jovian particles. As Jupiter's powerful magnetic field lines sweep through this conductive layer, they are bent and warped by the electrical currents generated within the Moon's air. This magnetic warping creates a protective bubble around the Moon, partially deflecting the incoming high-energy radiation and shaping the path of the escaping plasma. By studying how these magnetic lines bend around the world, scientists can deduce the exact electrical conductivity of the atmosphere and the hidden magma layers below. It reveals a complex web of interactions where the invisible forces of magnetism and electricity are deeply intertwined with the physical geology of the burning Moon. When we analyze the chemical signatures left behind by the massive volcanic eruptions, we encounter an unexpected ingredient that closely connects this alien world to the chemistry of Earth. Sophisticated spectroscopic measurements have revealed the presence of sodium chloride, the very same compound we know as common table salt, vaporized deep within the volcanic vents. This salt is blasted high into space alongside the sulfur gases, breaking apart under the intense radiation belt of Jupiter to feed the surrounding plasma cloud. The existence of these chloride compounds suggests that the interior of the moon contains ancient, volatile reservoirs that have survived billions of years of intense heat and recycling. Scientists believe that this salt might be a remnant from the moon's early formation period, a time before the intense tidal forces completely baked the world dry. It presents a beautiful chemical mystery, showing that even in the most extreme volcanic environments, familiar atomic building blocks continue to play a crucial role. The structural foundation that prevents this hyperactive world from tearing itself apart completely is a rigid outer shell known as the lithosphere. Planetary scientists estimate that this rocky crust stretches down to a thickness of between 30 and 50 kilometers, acting as a heavy lid over the churning magma ocean below. This lithosphere is composed of dense, fractured silicate rock that is continuously compressed and stressed by the immense gravitational forces of Jupiter. Because the crust is subjected to such extreme mechanical forces, it is thoroughly broken by a complex network of deep faults and fractures that allow magma to escape easily. Despite being continuously broken and melted from below, this rocky shell maintains enough structural integrity to support the towering 17-kilometer-high mountains that dot the landscape. It is a fragile shield caught between the absolute cold of outer space and the white-hot pressure of a world turned inside out. Among the hundreds of individual volcanic centers that define the face of this moon, Patara stands out as one of the most visually stunning examples of active geology. This unique volcanic cauldron is surrounded by an intricate web of colorful lava flows that resemble a brilliant, abstract painting stretched across the plains. The flows emerging from Kyolen display a striking transition of colors, shifting from dark silicate centers to bright green and yellow edges as the molten rock interacts with the surface frost. This green coloration is particularly fascinating to researchers, as it likely indicates a complex mixture of hot iron-rich silicates melting and blending with sulfur compounds. The persistent activity at this site shows how localized magma chambers can create unique chemical microenvironments, producing variations in lava composition that differ from the global average. Watching the slow advance of these multicolored flows provides a deep understanding of how fluid dynamics and chemistry combine to rewrite the alien terrain. A truly magical transformation occurs whenever the moon slides directly behind the immense bulk of Jupiter, plunging into a deep, celestial eclipse. Stripped of the blinding glare of reflected sunlight, the true luminous nature of this volcanic world is revealed to the waiting cameras of our spacecraft. The frozen plains disappear into total darkness, but the landscape suddenly comes alive with hundreds of glowing red points of light, marking the active lava lakes and open fissures. Above these glowing hotspots, The thin sulfur dioxide atmosphere begins to glow with soft, ethereal shades of blue, green, and red as it is bombarded by energetic particles. These spectacular auroral displays trace the invisible paths of the magnetic field lines as they twist through the gases, creating a ghostly light show that dances over the darkened volcanoes. It is a visual masterpiece that highlights the dual nature of the moon, revealing a world that glows with its own internal fire when hidden from the light of the sun. The volcanic activity of this restless world does not merely affect its immediate surroundings, but launches a continuous stream of matter deep into the interplanetary space of our solar system. Microscopic dust grains, composed primarily of sulfur and silicate crystals, are blasted high into the upper reaches of the thin atmosphere during explosive plume events. Once these tiny particles escape the weak gravitational grip of the moon, they become electrically charged by the intense radiation environment of the Jovian magnetosphere. Jupiter's rapidly rotating magnetic field then catches these charged dust grains, accelerating them to incredible speeds of over hundreds of kilometers per second. These high-velocity dust streams are hurled outward into deep space, forming a vast, invisible highway of cosmic debris that extends far past the orbits of the other moons. Space probes passing millions of miles away from Jupiter have detected the impact of these tiny volcanic messengers, proving that Io actively contaminates the wider solar system with its inner ashes. While the spectacular surface eruptions capture our imagination, a vast amount of the moon's volcanic energy is expressed through hidden, subterranean movements of magma. For every drop of liquid rock that breaches the surface to form a lava flow or a towering plume, an immense volume of molten material remains trapped within the crust. This magma forces its way horizontally between layers of older rock, creating vast underground networks of vertical dikes and horizontal sills that expand the crust from within. These massive subsurface intrusions generate intense structural pressures that push the overlying ground upward, causing the smooth sulfur plains to fracture and tilt. This hidden plumbing system explains how the moon can dissipate such an enormous amount of tidal heat without requiring every single square kilometer to be covered by active vents. It reminds us that the surface we observe is merely the outer skin of a deeply complex, churning engine where the most significant structural transformations happen completely out of sight. Another fascinating demonstration of planetary dynamics can be observed at the highly active volcanic center named Marduk-Patara. This dark, irregular depression is characterized by its highly unpredictable behavior, featuring volcanic vents that slowly migrate across the valley floor over the course of several years. Spacecraft observations have shown that the primary source of heat within Marduk constantly shifts, closing old fissures while ripping open fresh paths through the solid silicates. The plumes generated by this volcano are often highly asymmetrical, tilting and blowing in different directions, as the underlying vents alter their shapes and explosive power. This continuous wandering of the volcanic heart suggests that the local magma conduits are highly flexible, easily eroded and redirected by the immense pressure of the liquid stone. Marduk serves as a perfect example of a world without a permanent anchor, where even the focal points of volcanic eruption are fluid, drifting features that refuse to stay still. To unlock the deep secrets of this distant volcanic world, astronomers do not rely solely on space probes, but use the most powerful ground-based telescopes on Earth to monitor its daily behavior. By utilizing advanced adaptive optics on massive telescopes like the Keck Observatory in Hawaii, scientists can pierce through the distortion of Earth's atmosphere to capture clear thermal images of the moon. These observations allow researchers to track the sudden onset of massive thermal outbursts, mapping the birth of new lava lakes across millions of miles of empty space. Furthermore, giant radio telescope arrays like the Atacama Large Millimeter Array can detect the faint radio whispers emitted by the trace gases in Io's atmosphere. This continuous monitoring from Earth provides a vital, long-term record of the moon's volcanic energy output, ensuring that we never lose sight of its restless pulse between deep space missions. It bridges the immense distance between our home world and the Jovian system, turning a tiny speck of light into a living, breathing laboratory. When we contemplate the existence of the massive, 17-kilometer-high mountains that dominate the landscape, we must ask how such giant structures can survive on a world with a warm interior. On Earth, mountains are slowly broken down by the action of water, ice, and tectonic shifting. But Io's peaks are preserved by their unique, bone-dry composition. Because the intense internal heat has completely purged the crust of all water molecules and volatile gases, the rocks that form these mountains are composed of highly compressed anhydrous silicates. This complete absence of moisture prevents the deep rock layers from becoming slick or weak, allowing the jagged blocks to maintain their immense vertical height without collapsing under their own weight. The mountains are essentially giant, solid wedges of dehydrated granite and basalt, frozen into place by the bitter cold of space that chills the outer crust. They stand as magnificent monuments to a world that was baked completely dry by the friction of gravity structural giants that defy the surrounding chaos. The exact mechanism of how tidal friction melts the interior of this world remains one of the most compelling debates in modern astrophysics. Scientists utilize complex mathematical models to determine whether this intense heat is generated primarily within the shallow asthenosphere, or deep within the lower mantle of the moon. If the heating occurs mostly in the shallow layers directly beneath the crust, we would expect to see volcanoes concentrated entirely near the equator, where the tidal flexing is most pronounced. However, the presence of major active centers like T-Vastor near the poles suggests that the melting forces operate much deeper, affecting the entire global mantle uniformly. This deep tidal dissipation creates a continuous, balanced ocean of magma that wraps completely around the iron core, ensuring a steady supply of heat to every corner of the moon. This ongoing scientific inquiry reminds us that we are still uncovering the fundamental laws that govern how gravity can manipulate the hearts of distant worlds. The southern hemisphere of this restless moon hosts a fascinating volcanic center named Masubai, which has puzzled scientists with its highly irregular behavior. Unlike volcanoes that erupt from a single fixed opening, Masubai features a long fissure that seems to manifest new vents across its length over several decades. The plumes generated here leave a distinct, V-shaped streak of dark material across the bright plains, a visual mark that alters with every major eruptive cycle. Observations from passing spacecraft revealed that Masubai can remain quiet for years before suddenly unleashing a torrent of low-temperature lava that spreads over vast areas. This shifting nature suggests that the underlying magma reservoirs are wide and shallow, easily redirected by subtle changes in the structural pressure of the crust. It stands as a prime example of the unpredictable geography that defines this world, where a single volcanic name represents a constantly moving target. The ghostly atmosphere of sulfur dioxide is remarkably uneven, forming a patchy envelope that concentrates heavily around specific geographic regions. Because the air is primarily fed by active volcanic plumes and the sublimation of surface frost, its density is highest directly over the equator and near major thermal hotspots. In contrast, the polar regions and the areas far removed from active vents possess a near-perfect vacuum, where the air is thousands of times thinner. This extreme localization means that a traveler moving across the surface would pass through varying microclimates, stepping from pockets of relatively dense gas into completely empty space. This uneven distribution prevents the atmosphere from developing a unified global circulation system like those seen on Earth or Venus. Instead, it remains a collection of isolated gaseous domes, dancing independently under the immense gravity of the nearby giant planet. A profound question that occupies the minds of modern astrophysicists is whether this intense volcanic activity is sustainable over cosmic timescales or merely a passing phase. Current mathematical models suggest that the energy dissipated by the immense tidal forces is slowly changing Io's orbital distance from Jupiter. As the moon pumps energy out into space through its hundreds of hot vents, it experiences a subtle orbital migration, slowly drifting outward away from the gas giant. This outward movement is precisely balanced by the gravitational interactions with Europa and Ganymede, which work to maintain the strict Laplace resonance. If this delicate balance were to shift even slightly, the resonance could eventually break apart, allowing Io's orbit to become circular and its volcanic fires to cool forever. We are witnessing this world at a very specific moment in cosmic history, a golden age of gravitational friction that has lasted for billions of years, but remains subject to the slow evolution of the solar system. To better understand the chaotic energy of this world, planetary geologists categorize the hundreds of active vents into distinct classes based on their thermal signatures. The most common type consists of persistent, low-intensity hotspots that radiate a steady amount of heat through crusted-over lava lakes or small fissures. A second, much rarer class includes the spectacular volcanic outbursts, where massive fissures suddenly tear open to release immense volumes of high-temperature silicate lava over a few weeks. Finally, there are the cooler, purely sulfur-driven flows that ooze across the plains at much lower temperatures, acting like molten rivers of yellow and orange wax. This classification system reveals that the interior of the moon is not a uniform soup, but a complex, stratified engine capable of producing entirely different styles of volcanism simultaneously. It allows scientists to map the energetic pulse of the moon, organizing the surface chaos into a structured spectrum of planetary heat. Stretching across the equatorial plains is a remarkable volcanic structure known as raw patera, which provides an exceptional example of a shield-like landform on this alien moon. Unlike the deep, sunken cauldrons that dominate most of the landscape, raw patera features a series of long, radiating flows that spread outward from a central elevated vent. These flows extend for hundreds of kilometers across the yellow deserts, creating a vast, dark birdfoot pattern that is easily recognizable from space orbit. Detailed spectroscopic analysis suggests that these extensive flows are composed of a unique mixture of silicates heavily enriched with liquid sulfur compounds, allowing them to remain fluid at lower temperatures. The flat, expansive profile of this structure shows that volcanic material can sometimes build outward rather than collapsing inward, offering a rare variation in the moon's architectural style. It stands as a monument to the diverse ways that liquid rock and chemical elements can interact when subjected to the relentless pulling of planetary gravity. The chemical journey of sulfur as it transitions from the molten interior to the freezing surface involves a fascinating sequence of molecular changes. When sulfur is trapped deep underground at temperatures exceeding several hundred degrees, it exists as a dark, highly viscous liquid composed of long polymeric chains. As this molten material breaches the surface and encounters the extreme cold of space, these complex chains quickly break apart into smaller, simpler rings of atoms. This rapid crystallization process causes the color of the cooling material to shift dramatically, changing from an initial deep black to a rich crimson red, then to a vibrant orange, and finally settling into a stable pale yellow. This means that a fresh lava flow leaves a chronological trail of its own cooling history, painted directly onto the ground for scientists to read. It transforms the landscape into a living laboratory of thermal chemistry, where every shade of color represents a specific stage in the element's journey toward crystallization. The volcanic fury of this innermost major moon extends its influence far beyond its own borders, directly affecting the surface chemistry of its closest neighbor, Europa. The massive streams of sulfur and sodium ions accelerated by Jupiter's magnetic field are hurled outward across the orbital gap, slamming into the trailing hemisphere of the icy world. This constant cosmic bombardment implants dark, sulfurous chemical compounds directly into Europa's clean water ice crust, staining the frozen plains with long, reddish-brown streaks. Over millions of years, this cross-contamination alters the spectroscopic signature of the neighboring moon, creating a fascinating chemical link between a world of pure fire and a world of absolute ice. Scientists studying Europa must constantly account for this incoming volcanic dust, separating the native elements of the icy ocean from the ash drifted across space from Io's vents. It reminds us that in the grand architecture of planetary systems, no world exists in complete isolation from its celestial companions. For human engineers designing robotic missions to the outer solar system, this hyperactive moon presents a uniquely hostile environment that demands extraordinary precautions. The intense streams of high-velocity volcanic dust and charged ions act like a continuous sandblasting machine, capable of degrading the delicate optical lenses and solar panels of passing probes. Furthermore, the immense electrical currents flowing through the space environment can induce dangerous voltage spikes within a spacecraft's internal wiring, risking total system failure. Mission planners must carefully calculate trajectories that minimize the time spent within the core radiation belt, often utilizing quick flybys rather than long-term orbital missions. Despite these severe hazards, the immense mass of the moon is occasionally used as a gravitational slingshot, stealing a fraction of its orbital momentum to accelerate probes toward even more distant worlds. It is a dangerous cosmic gateway, a place where the rewards of scientific discovery are balanced against the very real threat of mechanical destruction. Nestled near the base of a towering, jagged mountain block sits an exceptional geological feature known to astronomers as Gish Bar Patara. This massive volcanic depression displays a highly irregular shape, bounded on one side by steep, collapsed walls that merge directly into the mountain's structural foundations. This close proximity reveals a profound tectonic relationship, showing how the immense horizontal compression that forces mountains upward also creates deep fractures that allow magma to breach the surface. The floor of Jishbar Patara is frequently flooded by fresh, dark silicate lava that pool against the ancient, dehydrated rock of the adjacent peaks. This creates a dramatic visual contrast between the sharp, towering shadows of the non-volcanic mountain and the flat, glowing expanse of the active cauldron below. It serves as a perfect natural laboratory for studying how vertical tectonic forces and fluid volcanic systems interact to shape the fragile crust under Jupiter's heavy grip. When we contemplate the ultimate destiny of this burning world, we look forward into a future governed by the slow, inexorable laws of orbital mechanics. The intense internal heating has already persisted for over 4 billion years, meaning this tiny moon has successfully dissipated an unimaginable amount of gravitational energy over its lifetime. Scientists believe that this hyperactive state will continue as long as the Laplace resonance remains locked, keeping the orbital path elongated and the internal friction alive. However, the slow tidal interactions between Jupiter and its outer moons are gradually expanding their orbits, a process that will eventually destabilize this perfect mathematical harmony millions of years from now. When that distant day arrives and the resonance finally breaks, Io will slide into a peaceful, circular path, allowing its volcanic vents to close and its magma ocean to freeze into solid stone. Until then, it remains a radiant, restless anomaly in the deep dark, a world destined to burn brightly as long as the giants dance around it. As the moon journeys along its elliptical path, the intensity of its volcanic activity experiences a subtle modulation based on its exact distance from Jupiter. When the moon reaches its closest point to the gas giant, known as Para-Jove, the gravitational pulling forces reach their absolute peak, stretching the inner mantle to its maximum deformation. Conversely, as it drifts to its furthest point, the tidal grip relaxes slightly, causing the interior pressures to shift and realign. This rhythmic pulsing acts like a planetary heart, squeezing magma chambers more intensely during certain phases of the short orbital cycle. Planetary astronomers have observed corresponding fluctuations in the brightness of specific thermal hotspots, hinting at a direct link between orbital geometry and volcanic output. It reveals a world whose fiery breath is perfectly synchronized with the cosmic distance it maintains from its massive master. Deep within the colorful expanse of the equatorial region lies Zamama, a highly dynamic volcanic center that showcases the diverse styles of Io's geology. This remarkable site features a central fissure that produces a steady, multi-directional flow of dark silicate lava, alongside a persistent, bright sulfur plume. The plume rises tens of kilometers into the dark void, spreading a delicate white blanket of sulfur dioxide frost over the surrounding dark lava fields. Over decades of observation, Zamama has shown a unique ability to maintain both explosive gas eruptions and quiet, effusive lava spreading simultaneously. This dual behavior provides scientists with an excellent example of a complex volcanic system where distinct plumbing lines connect to different chemical reservoirs. It stands as a brilliant reminder of the intricate internal variety that exists even within a single geological feature on this burning moon. Beneath the heavily fractured lithosphere, a fascinating geological process known as magma underplating helps to shape the broad topography of the plains. As heavy, magnesium-rich silicate melts rise from the deep mantle, they often fail to breach the surface crust immediately due to the weight of the overlying rock. Instead, these dense magmas pool at the base of the crust, spreading horizontally to form massive, hidden reservoirs of intense heat. Over time, the thermal energy radiating from these underplated layers slowly melts the lower sections of the crust, thinning it from within and causing the ground above to bulge. This underground inflation can trigger widespread cracking across the surface plains, opening fresh pathways for lighter sulfur gases to escape. It demonstrates that the visible landscape is constantly being sculpted by invisible sheets of subterranean fire that manipulate the crust from below. The vast fields of sulfur dioxide frost that blanket the landscape do not simply sit passively in the bitter cold, but act as a powerful thermodynamic regulator for the entire moon. During the brief daylight hours, the faint sunlight causes a fraction of this frost to sublime, absorbing thermal energy and keeping the local ground slightly cooler than expected. As night falls and the temperature plummets instantly, this vapor condenses back onto the surface, releasing its stored latent heat into the surrounding rocks. This continuous exchange of state buffers the extreme temperature transitions, creating a subtle thermodynamic cycle that ripples across the multicolored plains. Without this protective layer of subliming and condensing frost, the mechanical stresses on the surface rocks would be significantly more destructive. It reveals an elegant environmental balance, where a toxic chemical compound serves as a cooling and warming blanket for a world of fire. In recent years, the Juno spacecraft has provided humanity with unprecedented views of the moon's polar regions, using its advanced infrared mapping instruments. By orbiting over the poles of Jupiter, the probe has been able to look down onto the top and bottom of Io, capturing high-resolution thermal images of areas never fully seen before. These observations have revealed a dense cluster of previously unknown hotspots glowing brightly in the dark polar nights, proving that the internal heat escapes uniformly from all latitudes. The data from Juno show that these polar volcanoes behave somewhat differently than their equatorial counterparts, often featuring smaller but more stable lava lakes that burn with a steady intensity. This wealth of new information has allowed scientists to refine their global models of tidal heat dissipation, painting a complete picture of the moon's energy output. It reminds us that even after decades of study, the cosmos still holds hidden truths waiting to be revealed by our wandering machines. While the grand architectural theme of this world is defined by deep, sunken depressions, there are rare locations where small volcanic cones manage to rise above the flat plains. These features, known as pyroclastic constructs, form when explosive vents steadily blast fragments of solidified lava and ash into the airless sky over a prolonged period. Because the moon's gravity is low, the ejected particles fly far and wide, settling into gentle, broad slopes rather than the steep mountains seen on Earth. These miniature cones are often composed of dark basaltic glass and sulfur granules, creating small dark mounds that punctuate the bright yellow expanses. Their presence shows that under the right conditions, the moon's internal pressure can create localized, building eruptions rather than continuous collapse. They offer a delicate textural contrast to the vast, smooth plains, small monuments to the diverse expressions of planetary volcanism. One of the most profound scientific discoveries regarding the internal nature of this moon is the complete absence of an intrinsic magnetic field. Despite possessing a massive core composed of iron and nickel, the moon lacks the internal convective churning necessary to generate its own global magnetic dynamo. Instead, the world is completely enveloped by the colossal magnetic lines of Jupiter, which sweep past the moon at incredible speeds. This interaction induces a secondary, temporary magnetic field within the moon's conductive ionosphere and subterranean magma ocean. This induced magnetism warps the surrounding space environment, creating a complex electrical feedback loop that funnels charged particles directly toward the poles of Jupiter. It shows that Io is magnetically naked, entirely dependent on the overwhelming presence of its parent planet to define its interaction with the wider cosmos. The unpredictable and violent nature of this environment was vividly demonstrated by a massive, unexpected eruption at a site named Thorpadera. During the late stages of the Galileo mission, scientists noticed that this previously quiet and unremarkable region had suddenly unleashed a colossal volcanic outburst. A towering plume of gas and dust shot hundreds of miles into space, while a massive fissure tore open to release an ocean of high-temperature silicate lava. The sheer volume of material was so immense that it completely erased the pre-existing geography of the region, coating thousands of square kilometers in dark ash and yellow sulfur frost. This sudden transformation occurred over the course of just a few months, proving that the moon's plumbing system can completely rearrange itself in a historical blink of an eye. It stands as a stark reminder of the restless energy that simmers beneath the surface, capable of rewriting the face of the world without warning. The physical laws governing the behavior of fluids in low gravity allow for the creation of subterranean structures that are vastly larger than anything found on Earth. Within the expansive lava fields, molten silicate rock often forms insulated underground channels known to planetary geologists as lava tubes. Because Io's gravity is roughly 1/6 of our own planet's, the structural ceilings of these empty tubes can support immense spans without collapsing under their own weight. This means that beneath the colorful sulfur plains lie vast, hollow vaults that could stretch for kilometers in width and length, acting as silent highways for ancient magma. When these giant tubes eventually run out of molten rock and drain completely, they leave behind colossal underground networks that remain hidden beneath the crust. They represent a hidden dimension of the moon's architecture, a silent, subterranean labyrinth carved by the fluid dynamics of liquid stone. The many flat-floored depressions scattered across the landscape function as highly efficient thermal radiators, helping the moon shed its massive internal energy into the cold void. These caldera lakes are often covered by a thick, dark crust of cooling silicate rock that insulates the molten material simmering directly beneath. As the crust radiates its heat into space, it slowly becomes denser and heavier than the underlying liquid stone, creating a structurally unstable condition. Eventually, this heavy crust fractures and sinks back into the depths, exposing a fresh, glowing sheet of liquid lava that releases a massive pulse of infrared energy. This rhythmic cycle of crustal formation and overturn allows the moon to steadily release its tidal heat without suffering a catastrophic global meltdown. It is a beautifully balanced cooling system, a series of dark windows through which a world of fire breathes its energy out into the silent dark. When we examine the atomic composition of the volcanic debris, we discover a fascinating distortion in the ratio of sulfur isotopes across the surface. Millions of years of continuous volcanic escape and intense solar radiation have preferentially stripped the lighter forms of sulfur from the upper crust. This leaves behind a landscape heavily enriched in heavy sulfur isotopes, providing scientists with a clear geological ledger of the moon's historical mass loss. By analyzing these subtle isotopic variations, researchers can estimate exactly how much material has escaped into Jupiter's magnetosphere since the dawn of the solar system. This atomic footprint tells the profound story of an ancient world that is slowly but steadily transforming its fundamental chemical identity under the relentless stripping of space weathering. It reveals that the very atoms of the moon bear the scars of its long, violent relationship with the gas giant. Deep within the sunlit plains sits a highly mysterious volcanic center known to planetary geologists as Kainhikili Patara. This fascinating hotspot is characterized by its exceptionally high thermal emission, despite a total lack of towering, visible atmospheric plumes. Observations suggest that Kainhikili operates almost entirely through silent, effusive silicate eruptions, where liquid rock pools in deep subterranean chambers before oozing out onto the floor of the caldera. The absence of gas-driven explosions means that this volcano quietly releases its immense energy without generating the dramatic visual displays seen at Peel or Tivashter. It provides an excellent example of a stealthy thermal engine, maintaining a steady, white-hot intensity that can only be detected by advanced infrared instruments. This silent burning demonstrates that the moon can hide its most powerful energy sources beneath a calm, dark crust of cooling stone. The continuous escape of volcanic material from the moon plays a critical role in regulating the rotational dynamics of Jupiter's entire magnetosphere. As the ton of plasma stripped from Io every second spreads outward into the giant donut-shaped torus, it creates a massive physical drag on the planet's spinning magnetic lines. Jupiter must expend an enormous amount of rotational energy to accelerate this newly arrived volcanic cloud to match its own rapid 10-hour spin cycle. This continuous expenditure of energy acts as a subtle cosmic brake, slowly slowing down the rotation of the giant planet over immense stretches of time. It reveals a profound feedback loop where the geological hyperactivity of a tiny moon can directly influence the rotational momentum of the largest planet in our solar system. We are watching a cosmic ballet where the inner fires of a satellite echo through the magnetic heartbeat of its giant master. The relentless accumulation of fresh volcanic material creates an extraordinary process of crustal loading that drives the continuous recycling of the lithosphere. As meters of fresh lava and sulfur snow rain down upon the plains over thousands of years, the immense weight pushes the older surface downward into the hotter mantle below. This continuous downward sinking forces the deep basaltic rocks to experience ever-increasing temperatures and pressures, causing them to remelt into fresh magma. This fluid stone then rises back up through the complex network of faults, breaking through the surface once again to continue the endless cycle. The moon is essentially consuming its own historical crust from the bottom up, creating a closed-loop system where the past is continuously melted to fuel the present. This rapid geological conveyor belt ensures that the crust remains completely fluid and adaptable, never staying static long enough to grow old. Within the towering, umbrella-shaped plumes that rise hundreds of miles into space, a spectacular phenomenon known as volcanic lightning occasionally illuminates the dark void. As billions of microscopic silicate ash particles and sulfur crystals are blasted from the vents at high speeds. They continuously collide with one another in the airless sky. This relentless friction strips electrons from the dust grains, generating immense fields of static electricity that build up within the expanding cloud. When the electrical potential reaches a critical threshold, it discharges in brilliant, silent flashes of lightning that arc across the expanding plume filaments. Because there is no atmosphere to carry sound waves, these electric discharges occur in absolute silence, casting a flickering radiance over the colorful plains below. It is a stunning display of cosmic physics, where the raw mechanical energy of an eruption transforms directly into a silent storm of pure electricity. Rising majestically from the southern plains is the jagged architecture of the Euboea Montes, a towering mountain block that holds a remarkable record in planetary geology. This immense structure features a long, steep ridge that terminates in a colossal debris field stretching for tens of kilometers across the yellow desert. Scientists recognize this feature as the largest single landslide mass wasting event observed anywhere in our entire solar system, dwarfing any collapse found on Earth or Mars. The entire western flank of the mountain fractured under the strain of continuous seismic tremors, sending a mountain-sized wave of shattered silicate rock crashing down onto the plains. This vast blanket of rubble stands as a silent monument to the structural instability that plagues the grandest heights of this restless world. It reminds us that even the most massive rocky giants are vulnerable to the continuous, rhythmic shaking generated by the internal volcanic engines. While the spectral signature of the atmosphere is heavily dominated by sulfur dioxide, sensitive ground-based instruments have detected trace amounts of hydrogen sulfide gas lingering over the active vents. This chemical discovery indicates that despite the overall dry and parched nature of the moon, small pockets of hydrogen remain locked within the deep interior. This hydrogen likely dates back to the earliest epochs of the moon's formation, surviving as a primitive remnant within the deeply buried mantle reservoirs. When these trace gases breach the surface, they interact briefly with the intense Jovian radiation before being torn apart into their constituent atoms. The presence of hydrogen sulfide provides a valuable clue for scientists attempting to reconstruct the early history of the Jovian system, showing that Io was not always completely devoid of lighter elements. It adds a delicate, complex note to the volcanic recipe, a fleeting chemical whisper from a forgotten primordial past. The intricate gravitational connection between Io and Jupiter results in a slow but steady transfer of orbital momentum that gently pushes the moon outward into space. As the giant planet rotates rapidly beneath the slower orbiting moon, its immense gravitational tidal bulge pulls Io forward along its path, accelerating its orbital velocity. This continuous acceleration causes Io's orbit to slowly widen, expanding its distance from the gas giant by a few centimeters every century. This outward migration forces the moon to act as a cosmic parasite, slowly draining the rotational energy of Jupiter to sustain its own orbital energy. As Io moves outward, it drags its sister moons, Europa and Ganymede, along with it, maintaining the strict mathematical harmony of the Laplace resonance. This slow, majestic expansion ensures that the entire Jovian satellite system evolves as a unified machine, driven by the steady deceleration of the master planet. When advanced space telescopes observe the dark hemisphere of the moon during its passage through Jupiter's shadow, they capture highly detailed infrared emission spectra that reveal the true temperature distribution of the crust. These night-side observations allow scientists to separate the background heat of the plains from the white-hot intensity of the active volcanic vents. By analyzing the precise wavelengths of light radiating into the dark void, researchers can map the existence of thousands of smaller, previously undetected thermal anomalies. This detailed thermal map reveals that the moon's surface is constantly simmering with a low-level background heat that conducts outward through the thin lithosphere. It shows that even the areas that appear dark and peaceful to standard cameras are actually resting upon a warm, thin crust that never truly cools down. This invisible glow turns the moon into a radiant beacon in the infrared spectrum, a world that shines brightly in the dark of deep space. The energetic ring of plasma generated by the moon's volcanic breath does not remain confined to its immediate orbit, but flattens out into a vast plasma sheet that extends throughout the entire Jovian system. This electrified disk of charged ions tracks the rapid rotation of Jupiter's magnetic field, sweeping past the more distant icy moons like Europa, Ganymede, and Callisto. As this high-velocity volcanic wind strikes the frozen surfaces of these outer satellites, it drives complex chemical reactions within their ice sheets, creating dark compounds and thin atmospheric halos. Io functions as the primary heart of the entire Jovian space environment, pumping energetic particles that shape the radiation belts of its sister worlds millions of miles away. It establishes a profound, interconnected ecology across the mini-solar system of Jupiter, where the inner fire of a single volcanic rock dictates the environmental reality for a realm of pure ice. The naming architecture chosen by international astronomers for the surface features reflects the fiery and turbulent nature of this alien landscape. The International Astronomical Union dictates that the active volcanoes, deep pattery, and bright plains must be named after mythological figures associated with fire. The sun, thunder, and the underworld from various ancient human cultures. This poetic naming system brings names like Peel from Hawaiian tradition, Surt from Norse mythology, and Prometheus from Greek lore directly onto the multicolored maps of deep space. It creates a beautiful cultural resonance where human stories of primal creation and destruction are projected onto the most geologically active body in our planetary system. As we trace these names across the parched plains, we realize that human language has found a fitting canvas to describe a world defined by eternal fire and continuous transformation. The extreme thermal radiation emitted by the massive lava lakes creates localized zones of atmospheric inflation directly above the active volcanic depressions. While the global atmosphere remains exceptionally thin and fragile, the intense heat causes a massive local surge in the sublimation of surrounding sulfur dioxide frost. This creates a dense, temporary bubble of gas that hangs over the glowing cauldrons, acting like a localized high-pressure cell in a near vacuum. These warm gas pockets scatter light differently than the surrounding cold emptiness, creating subtle optical distortions that can be detected by sensitive space instruments. This localized inflation reveals how closely the physical state of the air is tied to the geothermal engines operating just beneath the crust. It represents a dynamic microenvironment where the extreme heat of the interior temporarily pushes back the freezing reality of outer space. When planetary scientists analyze the global positions of the giant atmospheric plumes, they observe a distinct latitudinal preference that reveals the internal mechanics of the moon. The majority of the high-velocity, dust-rich plumes are concentrated within the equatorial and mid-latitude zones, where the tidal flexing forces are calculated to be the most intense. These regions experience the greatest amount of horizontal stretching and vertical distortion as the moon sweeps along its elliptical path around Jupiter. This concentration of explosive energy near the equator suggests that the shallowest parts of the magma ocean are heavily influenced by the orbital alignment of the Jovian system. In contrast, the polar regions tend to feature more stable, effusive lava lakes rather than the towering, explosive fountains that paint the equatorial sky. This uneven distribution of volcanic styles provides crucial data for researchers attempting to map the exact pathways that magma takes from the mantle to the surface. The volcanic ash and gases that escape the weak gravitational pull of the moon contribute a specific population of heavy ions to the Jovian magnetosphere. Unlike the solar wind, which consists primarily of light hydrogen and helium ions, the space environment around Jupiter is heavily populated by heavy sulfur and oxygen atoms derived directly from Io's interior. These heavy particles carry a massive amount of kinetic energy as they are accelerated by the rapidly spinning magnetic field lines of the gas giant. This unique composition transforms the Jovian radiation belt into a highly corrosive environment, where the heavy ions can cause severe damage to any unprotected matter through the process of atomic bombardment. It means that the volcanic breath of a single moon reshapes the entire chemical and physical landscape of the space environment for millions of miles around. By analyzing this heavy ion population, space probes can read the internal chemical recipe of the moon without ever touching its burning surface. The periodic passage of the moon into the giant shadow of Jupiter alters the visibility and thermal signature of its active calderas in a highly predictable manner. When the blinding glare of the sun is completely blocked by the massive gas giant, the true thermal radiance of the plains becomes the dominant feature in the infrared spectrum. This regular transition allows orbiting spacecraft to measure the cooling rates of the crust with incredible precision, separating old lava flows from active volcanic vents. During these hours of darkness, the sudden drop in ambient temperature causes the gaseous sulfur dioxide to freeze out rapidly, clearing the atmosphere and offering a crystalline view of the glowing fissures below. It creates a stunning visual rhythm where the world transitions from a colorful, sunlit desert into a dark canvas, illuminated entirely by hundreds of white-hot volcanic eyes. This cycle of eclipse and illumination provides a perfect natural laboratory for testing how the alien crust responds to sudden thermal changes. The exceptionally high temperatures of the silicate lavas flowing across the plains provide a living window into the ancient geological history of our own home planet. The ultramafic lavas observed on Io, rich in magnesium and operating above 1600 Kelvin, are virtually identical to the ancient cometate lavas that shaped the Earth's crust during the Archean Eon billions of years ago. On modern Earth, the gradual cooling of the mantle has made such high-temperature eruptions impossible, leaving their remnants frozen in ancient rock formations. By studying the fluid dynamics and cooling behavior of these active flows on Io, geologists can directly observe the physical processes that built the foundational crust of the early Earth. It transforms the distant, volcanic moon into an operational time machine, allowing humanity to study the primordial conditions that existed before the dawn of life on our own world. The restless moon preserves a style of planetary heat that has long since vanished from the inner solar system. The internal structural mapping of the massive volcanic pattery reveals an intricate system of terraced walls that speak to a history of multi-stage collapse. As the immense underground reservoirs of liquid stone empty during major eruptive phases, the overhead crust does not fall down in a single, clean motion. Instead, giant concentric blocks of rock fracture along the edges of the depression, slipping downward in a series of steps or terraces over deep time. These structural steps can rise hundreds of meters above the caldera floor, creating a rugged and complex boundary between the flat lava plains and the elevated crust. The presence of these terraced formations shows that the lithosphere possesses significant mechanical strength, resisting the total collapse forced by gravity until the underlying support is completely removed. By analyzing the geometry of these giant steps, planetary structural engineers can calculate the exact depth and volume of the magma chambers that lie hidden beneath the surface. As the moon speeds along its orbital path through the intensely magnetized environment of the Jovian system, it creates a massive electromagnetic disturbance known as an Ulfane wake. Because the rapidly rotating magnetic field of Jupiter moves much faster than the moon's orbital velocity, it constantly sweeps past Io from behind, creating an intense relative motion. This interaction induces powerful electrical currents within the conductive ionosphere, warping the magnetic field lines into a complex, aerodynamic-like wake that trails behind the moon. This invisible, energetic structure extends for hundreds of thousands of kilometers through space, vibrating with intense plasma waves that can be detected by distant radio telescopes. It acts like a giant cosmic tuning fork, continuously vibrating the magnetosphere of Jupiter with every revolution of the volcanic moon. This phenomenon demonstrates that the physical presence of the moon alters the very geometry of the invisible energy fields that dominate the Jovian Empire. The precise measurement of trace noble gases and minor chemical elements in the thin atmosphere provides critical constraints on the total volatile loss experienced by the moon over its lifetime. Sophisticated orbital spectrometers search for signs of elements like argon, krypton, and molecular nitrogen, which are typically present in the interiors of primordial icy bodies. The extreme scarcity of these lighter, volatile elements confirms that the continuous tidal baking has been incredibly thorough, effectively purging the entire mantle of its original gas budget. This profound depletion forces scientists to conclude that the current volcanic cycle is operating almost entirely on recycled heavy materials that cannot easily escape the moon's gravity. It reveals a world that has been refined by fire over billions of years, leaving behind a highly concentrated distillation of rock and sulfur. The chemical emptiness of its air tells the grand story of a world that has completely outlived its original primordial atmosphere. When we contemplate the long-term evolution of this hyperactive world, we can trace a fascinating atomic journey where a single molecule of silicate rock is recycled multiple times through the planetary engine. An atom erupted as liquid lava at Loki Pateracools to form the solid floor of the caldera, only to be buried by fresh layers of volcanic ash within a few decades. Over the course of several million years, the continuous accumulation of material forces that specific rock layer deeper into the crust, sinking toward the warm asthenosphere below. Eventually, the intense heat and pressure remelt the solid silicate back into fluid magma, allowing it to join the subterranean ocean of stone once again. This recycled magma will eventually find a fresh fracture, rising back to the surface to erupt from a different vent and begin the entire cycle anew. This continuous, closed-loop conveyor belt means that the material of the moon is in a state of eternal reincarnation, driven by the inescapable grip of Jupiter's gravity. The continuous movement of this hyperactive moon does not merely shape its own destiny, but sends subtle gravitational ripples throughout the entire Galilean satellite system. As Io races along its innermost path, its mass exerts a rhythmic, microscopic pull on the outer orbits of Europa, Ganymede, and even distant Callisto. Over millions of revolutions, these tiny gravitational perturbations accumulate, preventing the outer moons from ever settling into perfectly tranquil paths. This constant, faint shaking helps to sustain the eccentricities of their orbits, indirectly feeding the tidal heating processes that keep Europa's subsurface ocean liquid. It reveals a beautiful chain of cosmic cause and effect, where the burning violence of the innermost moon acts as a mechanical heartbeat that stabilizes the habitability of its icy sisters. We are observing a deeply unified family of worlds, bound together by invisible strings of gravity that echo across millions of miles of empty space. The definitive proof of a global, subterranean magma ocean was achieved through a brilliant method of electromagnetic sounding conducted during deep space missions. As the immense magnetic field of Jupiter sweeps through the moon's interior, it induces powerful electrical currents within any highly conductive material buried beneath the crust. By carefully measuring the secondary magnetic fields generated by these internal currents, scientists confirmed that a vast layer of molten rock must wrap completely around the iron core. This churning sea of liquid stone is estimated to be dozens of kilometers thick, making up a significant fraction of the moon's total mantle volume. It serves as a fluid cushion that allows the rigid outer shell to decouple from the core, maximizing the dramatic flexing caused by tidal forces. This hidden ocean ensures that the volcanic engines are never isolated, but are instead part of a global network of liquid fire. Beyond the dominant presence of sulfur dioxide, sophisticated laboratory simulations and orbital observations suggest the existence of more complex chemical compounds like sulfur trioxide lingering across the parched plains. This highly reactive molecule forms under extreme conditions where intense heat breaks apart simpler volcanic gases just before they encounter the freezing vacuum of space. As these exotic molecules settle onto the multicolored soil, they interact with the surrounding sulfur frost, creating unique chemical polymers that alter the local surface texture. These complex compounds can only survive in the deep cold and low pressure of the Moon's environment, breaking down rapidly if subjected to the warm, thick atmospheres of inner planets. Their presence adds another delicate layer to the complex geological recipe of the Moon, showing that the volcanic vents function as immense chemical reactors that continuously synthesize rare elemental combinations. It reminds us that the alien landscape is painted not just with elemental rock, but with a highly specialized tapestry of cosmic chemistry. The unique structural behavior of the landforms reveals a fascinating balance between the low gravity of the Moon and the exceptionally high density of its silicate rocks. Because the gravitational pull is only a fraction of Earth's, large geologic features can maintain incredibly steep slopes and vertical cliffs without instantly collapsing under their own weight. This low gravity allows the walls of the deep volcanic pattery to stand as sheer, multi-kilometer drop-offs that would be physically impossible on a larger planet with a warm interior. However, this stability is continuously challenged by the relentless seismic tremors generated by hundreds of active vents erupting simultaneously across the globe. When a structural failure finally occurs, the dense rock falls in slow, majestic landslides that carry vast fields of rubble deep into the smooth plains. This creates a highly distinct topography where moments of extreme structural permanence are punctuated by sudden, slow-motion transformations of the landscape. The towering volcanic plumes that shoot hundreds of miles into the airless sky function as magnificent, natural planetary probes that allow scientists to sample the deep interior without ever drilling into the crust. By steering spacecraft directly through the outer edges of these expanding gas clouds, humanity has been able to capture escaping atoms that were trapped deep within the mantle just hours prior. This direct sampling method provides an unparalleled look at the isotopic ratios and chemical purity of a world operating under extreme internal heat. It eliminates the need for complex landing mechanisms, transforming the hostile space environment into a cosmic laboratory where the Moon actively delivers its own secrets to our waiting instruments. The data gathered from these high-altitude passes reveal a mantle that is exceptionally well mixed, continuously churned by the global tidal forces that prevent the interior from settling into stagnant layers. It shows that the Moon's violent eruptions are also its greatest scientific gift, offering a clear window into the deep heart of a rocky satellite. The physical movement of the volcanic Moon through the powerful magnetosphere of Jupiter triggers a spectacular phenomenon known as Jovian decometric radio emissions. These intense bursts of long-wavelength radio waves are generated as the electrified plasma torus interacts with the planet's magnetic field lines, creating a giant natural radio transmitter. Astronomers on Earth can predict the exact timing of these radio storms by calculating the precise orbital position of Io relative to our field of view. When the moon reaches specific angles in its path, it acts like a cosmic switch, opening a floodgate of radio energy that beams across the solar system. This remarkable connection demonstrates that the geological activity of a tiny moon can modulate the electromagnetic voice of the largest planet in our system. It turns the entire Jovian system into a musical instrument of cosmic scales, where the inner fire of a satellite plays a continuous melody across the radio spectrum. When we calculate the total energy balance of this restless celestial body, we discover a world that lives almost entirely independent of the warmth of the distant sun. The amount of thermal energy radiated by the hundreds of active hotspots and lava lakes completely dwarfs the faint solar radiation that reaches this cold region of space. This immense excess of heat means that if the sun were to suddenly go dark, the volcanic moon would continue to shine brightly in the infrared spectrum, unchanged by the cosmic dark. Its climate and geological reality are driven entirely from within, fueled by the relentless friction of gravity rather than the light of a star. It stands as a profound philosophical example of an independent world, a place where planetary life is sustained by the invisible embrace of its neighbors. This independent thermal existence highlights the supreme power of tidal forces, which can transform a frozen corner of the solar system into a beacon of primal energy. The exceptionally harsh radiation environment surrounding this hyperactive world serves as the ultimate baseline for testing and modeling the survival of future space exploration missions. The intense bombardment of heavy sulfur and oxygen ions, accelerated by Jupiter's magnetic field, presents a mechanical and electrical challenge that is completely unmatched anywhere else in the solar system. By studying how the moon's thin atmosphere and induced magnetic field respond to this relentless particle storm, engineers can design better shielding for probes destined for nearby Europa and Ganymede. The data collected near Io provide a worst-case scenario that helps to map the invisible boundaries of the Jovian magnetosphere, ensuring that future life-seeking missions can survive long enough to unlock the secrets of the icy moons. It transforms this burning desert into a vital protective shield of knowledge, a dangerous proving ground where humanity learns to navigate the lethal currents of the deep cosmos. It reminds us that every hazard encountered in this volatile domain offers a profound lesson that illuminates the survival of exploration across the wider solar system. Detailed mathematical analysis of the global heat flow has revealed a fascinating variation in the structural thickness of the moon's rigid outer crust. Because the tidal flexing forces are mathematically concentrated near the equatorial regions, the internal melting is most intense directly beneath the moon's midsection. This causes the lithosphere to be significantly thinner at the equator, sometimes measuring only a few dozen kilometers before transitioning into the churning magma ocean. In contrast, the polar regions experience less direct stretching from Jupiter's gravity, allowing the crust to cool and thicken into a heavier, more stable lid. This structural variation creates a hidden, oval-shaped interior geometry that influences how magma forces its way to the surface across different latitudes. It shows that the world is structurally contoured by the invisible hands of gravity, possessing a deep architectural asymmetry that shapes its global volcanic personality. As we complete our journey through the 100 profound insights that define this volcanic masterpiece, we realize that Io operates as a magnificent, gravitational perpetual motion machine. It exists in a permanent state of crisis that is perfectly stabilized by the immutable laws of orbital mathematics and fluid dynamics. Every river of molten silicate, every towering purple aurora, and every silent landslide is a direct expression of a giant planet's weight compressing a tiny sphere of rock. It stands as the ultimate bridge between the cold, orderly geometry of celestial mechanics and the hot, chaotic reality of active planetary geology. This restless world reminds us that the universe does not remain static or dead in the outer dark, but can kindle a fire of absolute intensity using nothing more than the invisible pull of space. We leave this burning sanctuary with a deep appreciation for the boundless creativity of gravity, a force that can turn a simple moon into the most hyperactive furnace in the cosmos. As we slowly pull back from the colorful plains and glowing cauldrons of Io, the chaotic fires begin to fade into the vast, dark tapestry of the Jovian Empire. The towering plumes of sulfur dust, the walls of liquid silicate fire, and the restless fractures of the lithosphere shrink into small, radiant points of light against the deep black of space. We look back one final time to see this small, hyperactive world completely enveloped by the magnificent, swirling amber bands of Jupiter, a silent master watching over its burning servant. The intense radiation belts and the humming plasma torus grow quiet in our perception as the distance widens, leaving us in a state of tranquil contemplation. We realize that the extreme violence we witnessed on the surface is merely a passing ripple in a much larger, beautifully ordered gravitational dance that has persisted for billions of years. This planetary machinery reminds us that everything in the cosmos is interconnected, bound together by the invisible, gentle pulling of gravity that shapes both the hearts of moons and the paths of stars. Io burns brightly not out of malice or chaos, but because it is answering the immutable mathematical laws of the universe, a perfect lock shared with its icy sisters, Europa and Ganymede. It is a profound testament to the creative power of nature, turning the cold friction of space into a radiant fountain of primal energy and constant renewal. In the grand architecture of the solar system, this restless moon fulfills its destiny with absolute precision, recycling its own past to sustain its brilliant presence in the dark. As the details of the sulfur plains dissolve completely into the shadows, a deep, overriding peace settles over the Jovian system. A quiet harmony where even the most violent fires find their place within the orderly motion of the heavens. We leave the volcanic jewel to its eternal rhythmic flexing, drifting further out into the cold, silent vacuum where the stars shine with a steady, unblinking light. The heavy weight of Jupiter, the electrical currents of the flux tube, and the roaring fountains of magma are now nothing more than a distant whisper. A soft lullaby hummed by the forces of gravity across the empty miles. The cosmos stretches out around us in every direction, an infinite, peaceful sanctuary that remains untouched by the fleeting anxieties of time and change. The mind can now rest completely, letting go of the heat and the motion, sinking into the deep, dark silence that binds all worlds together. Sleep well among the stars, cradled safely by the eternal laws of the universe, as our long journey concludes in absolute peace, stillness, and tranquility.